Hey guys, I'm Tio, your quantum group professor. This is the first of a series of 6 lectures on quantum groups, an introduction to all this. It's a kind of like a graduate course, of course, entry-level graduate course. So if you know your calculus, you'll be just fine. And the end of the game is to present the theory in 6 1-hour lectures. We try to keep it 1 hour. There are, of course, many things that can be said about these quantum groups. So it's quite recent. So it's 30 years old, which means in mathematics very, very recent stuff. And there's a lot of research going on. So very interesting things, mathematics and physics, somehow in the middle, mathematical physics. So let's find this presentation first. Here we go. So operator algebras and non-commutative spaces, that's going to be our first lesson today. As I was saying, so there are 6 things in the series. So this first one is about operator algebras. There won't be actually many quantum groups here. And the quantum groups will start with the second lecture. Okay, so the plan is, this is operator algebra, something which is really needed. No matter what you do, mathematics, physics, you'll get at some point to these things, operator algebras. So it's very useful. And then second lecture will be quantum groups, introduction, using all this. Lectures 3, 4, basic stuff, 4 more advanced, 5 more advanced, and then 6 ununderstandable. Okay, introduction to research. So this is it. Now what we're going to do today is operator algebras. Hilbert spaces, linear operators. We're interested in operators on Hilbert spaces. This means somehow infinite matrices. So this is linear algebra in infinite dimensions, what we're doing today. And that's, of course, very interesting in mathematics, physics, all branches. I mean, you know, this linear algebra, that's along with calculus, that's the pride of mathematics. That's why we teach it in undergrad school. And now, if you're getting to the grad level, well, you have to extend that to infinite dimensions. That's obviously very interesting. So that's an introduction here today to all this material, or at least, well, the most somehow beautiful and accessible things there. So we'll do this somehow, take these operators, understand the eigenvalue theory. This is called spectral theory, okay, in this setting, infinite dimensional. Spectral theory and operator algebras. So these are algebras formed by these operators. And there are 3 theorems about them, which are very basic, of Gelfand, GNS, and the finite-dimensional case. We'll have all these three theorems with proofs here. That will be the main thing that we'll do today. Okay, so we'll learn all these 3 theorems that you need in order to do sister algebras. And finally, we'll talk a bit about non-commutative spaces. Like once you have these sister algebras, you can talk about non-commutative spaces, for instance, some kind of free spheres, free tori, and this will be a good introduction for the next time. Next time we'll enlarge the list from sphere tori also with groups somehow, and these groups will be the quantum groups. That's the idea. Now let's get it started. Hilbert spaces, you know all this surely. So that's a complex vector space. Okay, it's complex. Everything is complex. And why complex? Because we're mostly interested in quantum mechanics, and there things are complex. Elementary particles have infinity of coordinates somehow, which are complex. Okay, so that's why I need complex numbers for physicists here. Quantum mechanics, so always complex. And scalar product, of course, so it must be linear at left, antilinear at right. So this is the convention that we use here. Positive, and then importantly, it must be complete with respect to this norm coming from Cauchy-Schwarz. So that's something that you know. Once you have 1, 2, 3, these conditions here, you can prove Cauchy-Schwarz, which tells you that this thing, well, it's a norm. So fourth axiom is that H must be complete with respect to this norm. Complete means Cauchy sequences converge. Now, what are the basic examples? Of course, Cn with the scalar products. Now, if you have Cn are just sequences, like a vector is a sequence of n elements, right? Complex numbers. Why not taking infinite sequences? So that's your L2 of n, it's called. same scalar product. More generally, if you take a measured space X, you can take L2 of X, L2 functions, complex always, okay? With the scalar product, so let's see some examples. If I take X, for instance, to be C to the N, okay? The counting measure, of course, I get this space. Also, I get this if I want to. So this is somehow the most general example, L2 functions, okay? Always remember that when you're given a Hilbert space, it's probably some L2 space. Now, the theory, what we need is especially Gram-Schmidt. So this tells you that once you have a basis, you can always orthogonalize it, okay? So every Hilbert space has a basis because of this. Just take an arbitrary one, apply Gram-Schmidt. So having a basis, this means that everything is uniquely determined by that basis. So H is actually L2 of I, okay? Now I is the index for the basis. So when I is countable and infinite, of course, H is called separable. So that's somehow the interesting case. And the separable space is unique, of course, because there is only one countable set. I mean, you can call it N or Z. I mean, they're all the same in bijection. So there is only one separable Hilbert space, and that's the one we're interested in. The problem now, there is a subtlety here, is that this space can take many forms somehow. For instance, if you take L2 of 0, 1, Weierstrass tells you that the powers, x, x2, x3, and so on, form an algebraic basis. So you can come with Gram-Schmidt, orthogonalize that, and you get your basis and an isomorphism to L2 of n. But the subtlety is that Gram-Schmidt is it's difficult for these polynomials. So actually that's an excellent exercise. So I guess all of you know all these things, but maybe some of you haven't tried to find the basis for L2 of 0, 1, so do it, okay? So start with Weierstrass and try to apply Gram-Schmidt to orthogonalize. You'll see it's not easy, and you might not get it actually. I might go to Wikipedia afterwards. The orthogonal polynomials is a keyword. If you don't find the formula, go there after some computations, orthogonal polynomials. So it's hard, and this means somehow that this separable Hilbert space that we're interested in, it might be unique, but when it comes like this as a L2 of 0, 1, that's it. I mean, there's no very explicit basis. So it's a subtlety here, okay? One unique space, but it can take many forms. And in general, the Hilbert space is, yeah, L2 functions. That's somehow the spaces that we're interested in. Now, we want to do linear algebra, okay? So, well, let's first take a basis, H Hilbert space with basis. Then, of course, the linear operators T from H to H are infinite matrices. I mean, you just, that's the coefficients, okay? As in the finite dimensional case, you call M this matrix, T, Ej, scalar Ei, and you have a correspondence and embedding like this. Well, in finite dimensions, of course, it's an isomorphism. You all know that linear maps is the same thing as matrices, and that's the connecting formula. In the infinite case, you only get an embedding because, well, not any matrix defines an operator. Things must converge with respect to the L2 norm. Okay, so you don't have all the matrices, just some of them. Now, in the infinite separable case, which is the one we're interested in, so L of H embeds into M infinity of C. So M infinity, don't be scared about this. I mean, it's just the matrices, but you allow them to be infinite in this sense here. Okay, not infinite in all directions, just like this. I mean, 1, 2, 3, 4, 5. The n is here as indices, horizontal, n is here, so the matrix is infinite like this. Okay, so operators finally are infinite matrices. Now, the problem is that what we've seen before, you see with Weierstrass, all that exercise to be done, so just not to use actually this interpretation of operators, because yeah, bases are something quite subtle for spaces of functions. So somehow the philosophy is that to think of operators somehow as objects on their own. You'll learn how to do that. Now, we'll be interested actually in bounded operators. So take an operator and you define this thing. It's the norm. As for matrices, it's the same formula. So sup over vectors of norm smaller than 1 of Th. That's a norm. And can be finite or infinite. So we're looking, an operator is called bounded if the norm is finite. And these operators, so they form a complex algebra with unit B of H, which is complete with respect to the norm. I mean, Cauchy sequences converge, so-called the Banach algebra. Then you have an evolution exactly like for matrices, the adjoint matrix. So that's the formula, okay? The usual one for matrices defines an evolution, and the norm and evolution are related by this formula, which for matrices, what does it say? So the norm is the biggest eigenvalue, absolute value, okay? So the biggest eigenvalue, yeah, it's trivial. Okay, so it's like z bar equals to z absolute value square, z being the biggest eigenvalue. Somehow all these things are clear in finite dimensions, okay, for usual matrices. Now in general, let's see how the proof goes. Yeah, same thing. So complex algebra, well, if you compose things which are bounded, or some, of course, is bounded. Now just write it down. Norm closed, take a Cauchy sequence of operators. Then these guys here, for any vector x, Tn of x will be Cauchy. So H being Hilbert, it's complete. So it has a norm, it has a limit. The sequence, you call it Tx. So that's your defined for any x. Works. Now evolution, let's go back here. So you see, given any vectors xy, this guy here, Tx scalar y, is linear in x. So it must be the scalar product of x with something. That's something, you call it T star of y. And that's your T star, okay? It's well defined. And well, when you say evolution, you have to prove a number of things like Ts star is a star T star, or T star star again is T. These simple things, they all follow from this. I mean, no problem. It's like exactly for matrices. And the last thing, so this was clear for matrices. In general, you don't have eigenvalues. So yeah, do by double inequality. Play a bit with this formula, you get your two inequalities, and you're done. One more remark in the matrix setting. So we don't really want to use matrices, but it's always somehow good to have in mind that these are matrices. This thing here is just the usual adjoint operation. I mean, if you go back, Mij, these were the coefficients. So you see, these guys are some Mij's here, Mij bars here. So actually, you get the formula for the adjoint matrix. So these are infinite matrices, but you can still do this. I mean, you flip the matrix and you put bars everywhere. So that's your operation. Now, sister algebras. So what we proved here, this theorem, so what we have, complex algebra with unit, norm evolution, and this formula. Let's call it sister algebra, okay? Sister algebra is exactly this, complex algebra with units, with norm, making Banach algebra with evolution, and this key formula is satisfied. So this comes from D of H, what we found, and with this definition, I mean, this theorem is just one line, half of a third of a line, a quarter of a line. D of H is a sister algebra, okay? That's what we proved here. So that's something that we know, B of H. Now, if you take any subalgebra which is closed both under the evolution and the norm, of course, it's gonna be a sister algebra, right? And we'll see later, but this is not trivial. This is going to be one of our three main theorems about sister algebras, that any sister algebra appears in this form. So you see that I have no Hilbert space here. We start to these axioms here, which are purely algebraic somehow. And well, we'll be able to prove that, in fact, these are exactly the algebra of operators. Very important results. The so-called GNS theorem. Now, another basic example is C of x, x being a compact space. Why? Because what do we need? Norm, that's a sup norm. It's complete, you all know. An evolution, you just put the bar on the function. So is this satisfied? Yeah, of course. At any point at the supremum, it's z bar is z to the square in norm. So it works, and it's commutative C of x because product of functions, of course, commutes. Fg is gf, right? And we'll see later that's the second main theorem called the Gelfand theorem, that any commutative sister algebra is of this form. Very important result. Now, one more thing. So there are three main results. The first one, second one, and the third one is about finite-dimensional sister algebras. So we already know from here that matrix algebras are sister algebras. You can sum them, remains a sister algebra. And the theorem will say that any finite dimensional system algebra is a direct sum of matrix algebras. This is the third theorem. So that will be the plan for today. Basically, we'll learn these three things with proofs and a few extra things like a bit of an introduction to non-commutative geometry and spaces and quantum groups. So let me tell you right away that non-commutative geometry, where it comes from the middle theorem here. So commutative system algebras are C of x being compact. Now, when you see this, you say, well, if I take an arbitrary system algebra now, which is not necessarily commutative, I can think of it as being C of x, with x being a kind of non-commutative compact space, okay? So this will be our non-commutative space. It's just somehow the duals of the system algebras. And we'll see that we have like, we'll develop a bit theory for spheres, tori, and then groups, starting from the next lecture. These are the so-called quantum groups, okay? So we have these three theorems. We really definitely need all three of them for doing things with the system algebras. And somehow we're most interested in the second one. And that's why we'll actually start with the second one. So the plan will be first proving this second one, then we'll go to this, the GNS, and finally the finite dimensional case. So let's try to prove all this, and in particular the second one. How to do it? Spectral theory. So remember, these guys, operators, are infinite matrices. So what to do is clear. I mean, we know all this linear algebra, which is really amazing, right? Have calculus and linear algebra. These are the main things that you learn in undergrad school. So eigenvalues or that, let's try to extend this to this setting. This will be our tools for dealing with operators and system algebras. So how to do it? We don't really have a notion of eigenvalues, okay, in infinite dimensions. So we have to do this. You take the spectrum, is the lambda such that A minus lambda is not invertible, lambda complex numbers. So it's somehow, well, for matrices, you obtain the eigenvalues. More precisely, the eigenvalues set, okay? So that's the subtlety. For matrices, you have all these eigenvalues. In general, for infinite matrices, you cannot talk about eigenvalues somehow separate. Well, you can, but later, more complicated. But you can talk about the set formed by them. Okay, it's the set of eigenvalues that we'll be using. This will be our main tool. Not the eigenvalues themselves, but rather the sets that they form. And this is the so-called spectrum. Other example, if you take, okay, so that was for matrices. For compact spaces functions, the subtract lambda function must be invertible, so lambda must not be in the image. Okay, you obtain the image. Now, the first theorem, you know that spectrum of AB, spectrum of BA for matrices, right? Eigenvalues are the same. Same happens here in this general setting, but outside zero, so there might be some problems there at zero. So theorem states that these sets coincide in the complex plane outside zero. They might not coincide with zero. So as the proof, you pick your lambda different from zero. By scaling, you can assume that lambda is 1. So basically, you have to prove that 1 minus IB is invertible if and only if 1 minus B is invertible. That's your proof. It's actually kind of tricky. So it's in order to find this, whenever I teach classes, I give this to students after 10 minutes. Sometimes they find, sometimes they don't. It depends on the year. And I give them the proof, and actually myself too. I think when I was a student, I tried to do this. I couldn't find it, so I had to look it up somewhere. So yeah, very tricky. So bad that I give you this. Should have given you this as an exercise. So it's true. Now this works, as I told you, lambda I rescale first to assume that it's 1. So it's 1 for lambda 0. And that lambda 0 is wrong, actually. So for matrices, it's obviously true, right? AB, BA. Same eigenvalues. So in infinite dimensions, if you take L2 of n, okay, basis was 0, 1, 2, 3, the Dirac mass is there. You take the shift, okay, shifts that right by 1. S star is the adjoint, goes in the other sense. Now, if you compose in one sense, S star, that's the identity, sure. Now, if you do it in the other sense, now S star, there's a problem there at 0. Okay, so it's different from 1. So we have this and this, and this means that S star and S star S, one is invertible, the other one is not. And so one has 0 in the spectrum, the other not. Very good. So we proved our first theorem. once again, the fact that it's a one-line proof doesn't mean it's trivial. Okay, so maybe after that, yeah, try to reprove this after the totals. Yeah, it's quite funny. So that's our first theorem. Now our second one, another thing that we know about matrices is that the eigenvalues of the square of the matrix are the squares of the eigenvalues, and same for cubes, inverses, even exponentials, sinus, all kinds of functions. So let's do this in this setting. And well, I have to be a bit modest here, because when you define the exponential of a matrix or the sinus, you have to, it's complicated, you have to do some analysis there. So I'm not ready yet for such things, okay? So we'll just do it for polynomials and more generally for rational functions. What's a rational function? Just the quotient of polynomials, p over q. So we want to prove that given a function f, polynomial or more generally rational, spectrum of f is f of spectrum, okay? Now, in order for this to make sense, f of a must make sense. So we need to write something like this, okay? So, well, this will be, of course, p of a multiplied by the inverse of q of a, right? This fraction. But q of a must be invertible, that's the main point. And for it to be invertible, the roots must not be in the spectrum, okay? When you decompose q and with the roots and you plug in a there, everything must be invertible, okay? So now the roots of q are called poles of f, of your rational function. So finally, that's your assumption. F must have poles outside the spectrum for this thing to be defined, f of a. Once it's well defined, you can write this formula and theorem, it's true. So let's say how the proof goes. Well, for polynomials, you just decompose and into factors. You see all these guys must be invertible. So if the product is invertible, all the guys must be invertible. That's what you use and you're done. Now rational functions, well, you get it from polynomials with the trick. So let's take a rational function p over q, and the lambda, which is, we want to prove this is equivalent to this, lambda complex. Let's just take this polynomial p minus lambda q. And then you see lambda is in the spectrum of f of a. Somehow by rescaling, if and only if 0 is in the spectrum of f of a. And now by using what we had this for polynomials, that's the same as 0 in f of spectrum of a. And you're done. Okay, so the for polynomials, it follows by decomposing a polynomial, and for rational functions, just follows from polynomials by taking this guy here. It's a trick. Very good. So we have this spectrum of f is f of spectrum for the moment for rational functions. Later, they'll become continuous or more complicated. But for the moment, that's what we need. Very good. Now, what else do we know about matrices? If you take a norm 1 matrix, the eigenvalues are smaller than 1, right? Of course, norm is the biggest eigenvalue. Also, if you take a unitary matrix, the eigenvalues are on the unit circle. That's something that you know. Take a self-adjoint matrix, the eigenvalues are real. And finally, the spectral radius, this means the radius of the smallest disk centered at 0 in the spectrum. So we complicate, that's the biggest eigenvalue somehow is equal to the norm. So that's something that you know too. In our setting, everything works fine. So that's the theorem. So once again, norm 1, unit disk, unitary on the unit circle, self-adjoint spectrum is real. Here the fourth item is a bit more technical, so you have to define a spectral radius like this, okay? The theorem is that it's equal to the norm in the case where the element is normal, commutes to the adjoint. Okay, so it's a bit tricky here, the fourth item. So let's see how the proof goes. It's like for the matrices. So first one just follows from this inversion formula, right? To prove spectrum of norm 1 is in a unit disk, you need to invert something. That's what you need. This formula works in any Banach algebra. Second thing, unitary spectrum is on the unit circle. Value z minus 1 is functional calculus for rational functions. Okay, that's a rational function, 1 over z, right? Question of polynomials. So what you get, you see here, I use the unitarity of A. So I get that the spectrum consists of numbers whose inverse are the conjugates. Well, that's exactly the unit circle, and you're done. Now, once you have this, let's prove now self-adjoints. So you see, you can get it from unitaries. The point is that We can pass from the unit circle to the real numbers by using this function, z plus it over z minus it real, okay? And so basically it's clear, I mean, this passes from the circle to the real line. So if we apply this thing here to what we found here, you get your result. Finally, the fourth thing, so spectral radius of a normal element equals the norm. In one sense, so we have this inequality, right? That's clear from one. Now, in the other sense, it's a bit tricky. Use the Cauchy formula in this way. Apply norm, taken roots, you get to this. Okay, so this converges to this and this to this. Now we're almost done. So remember, we have an inequality, and this is more or less the converse inequality. But we will still need to have normal phi here instead of these guys. Okay, that's the only thing left, to replace these things here by normal phi. And how to do? Well, in the self-adjoint case, you just use this formula. So this means that norm of a square equals to the norm of a to the square. So this means that all these guys, at least for powers of 2, are it's stationary in the convergence. Okay, so you have norm of a everywhere you're done. In general meaning for a normal element, you use this and you get it from the self-adjoint case. Very good. So we have this spectra. Good. We can prove our first main theorem, Gelfand. So remember, C of x with x compact space is commutative system algebra, right? Subnorm and bar as an involution. And this is the converse. Any commutative system algebra is of this form. So how to do it? Have to think at C of x. So given C of x, how do you reconstruct x? Take the characters of C of x, meaning maps to C which are linear multiplicative, okay? Continuous. And these characters are exactly the Dirac masses are the point of x, right? So that's how you reconstruct x out of C of x. And generally do the same. So let's define a spectrum to be the space of characters. Topology on it, making continuous the evaluation maps. It's compact, no problem. And also we have a morphism given by evaluation. So finally, we're almost there. We have to prove that this is an isomorphism, okay? And that's what we have to prove. A goes to C of x, x being the characters. So morphism, it's linear multiplicative. Now, for involutive, it's a bit complicated. That's quite tricky. You might miss it when you prove it. You just forget about involutivity. In fact, we're going to use here all the spectral theory that we learned. So, first of all, you have real and imaginary parts in these algebras. Okay, it's like for numbers of matrices, right? For matrix, you can always decompose it. Same formula here. So now you can reduce the attention to the real case if you want for such problems. So you want to prove this, and it just follows from the fact that the spectrum is real. Okay, so we're using here this, which actually uses this. Was the proof? We are using this, which use this plus functional calculus here. Basically using everything here for this small little thing that every symbol use. It's quite funny. Yeah, small thing that you might forget about and you actually complicate it. You know this theory. Now, what else? We have a morphism. Well, we want to prove now that it's isometric. Well, that's the spectral radius formula. So remember, our algebra is commutative, so any element is normal in particular because it's commutative. So you can apply this thing, spectral radius equals the norm. That was the Cauchy thing, okay, the complicated one. And that's what you get, isometric. And finally, isometry means injective, of course, in particular, and surjective from Stone-Weierstrass because characters separate points. So very good. We have our first theorem, Gelfand theorem. Commutative system algebras are exactly C of x. As I was telling you, yeah, the main application will be non-commutative geometry, but this will come in a second. Let's have some operator algebra applications of this first. Okay, so first, continuous calculus. We know that this formula is true for rational functions. Okay, I told you for continuous it's a bit more complicated. And here is how it works. So assuming that A is normal, importantly normal, and let F be a functional spectrum, then this is true. Yeah, of course, f can be defined, f of a can be defined as the first item. So the proof goes together of all this. So the idea is that since A is normal, the algebra that A generates is commutative. So all the theorem, the statement lives there in that system algebra. So in the commutative case, so by Gelfand, we're actually dealing with functions, okay? So it's over. Functions can compose them and apply if you want square roots to them, no problem. So you have all these formulas, okay? Again, A is normal, meaning that algebra generated by this commutative by Gelfand. It's just functions, so we're done. Very nice. Now positivity. One more thing. So matrices, right? Positive ones are those having positive eigenvalues. So here, pretty much the same happens. So the following are equivalent, and these are the so-called positive operators. Spectrum is formed of positives. It's a square of a self-adjoint, or it's EC star for some C. Well, this is true. So 1 implies 2. Well, spectrum is real, your self-adjoint, algebra is commutative, and by Gelfand can extract the square root, right? It's this thing here if you want. Or just plain Gelfand. I mean, that is we need the square root here, right? Is b squared. So the square root for functions, we don't know. So we're done with Gelfand. Now 2 implies 3, of course, the B is trivial. 3 implies 1 is tricky by contradiction. So the idea is that you multiply first your element by something and get minus d star greater than 0. On the other hand, d star d greater than 0 by this computation. And the problem is that, so greater than 0 means that the spectrum is positive. So there's somehow to this bizarre conclusion that this d star at the same time the spectrum must be positive or negative. And rather d star and d star d, sorry. Wrong here. D star and D star D. So D star has positive spectrum, D star D negative. That's a contradiction because remember spectrum of AB is spectrum of BA. That was our first theorem outside 0. So you can apply this to D and D star and you get your contradiction. Okay, so quite tricky all this. Have positivity, very good. So pretty much done. I mean, what can we do else? Let's think a bit about it. So for matrices, we have I told you cannot really speak about eigenvalues, just about the set formed by them. And what we have, the spectrum, we have this functional calculus, which is rational, continuous, positivity. Yeah, that's decent. I mean, if you're looking now for more complicated things that you know about matrices, all these tricky decompositions like Danforth, whatever, Jordan, it's going to be hard here. Also, we don't have a determinant. So I mean, the basic theory somehow stops here. If you want to advance, it's going to be hard. You have to read books, okay? And that's pretty much it. Now, let's go to what we're interested in, non-commutative spaces, okay? And this will lead us to quantum groups. So what's the idea what I told you? So Gelfand says that commutative case means C of X. Now in general, let's just write it that C of X, X being a non-commutative space. So what's this? Is this even correct? I mean, what the hell? And, I mean, if you take the usual matrix, is a man of C, for instance, is your algebra, and write it as C of X. What was the dumb space there? X. I mean, you cannot see it, right? Matrices are not really functions of a space, so this is a bit abstract. So let's go slowly. So first, have to decide if we are mathematicians or physicists. Well, let's be first mathematicians, okay? We're more picky. So as a mathematician, we will certainly disagree with this, right? Space must have points, so this won't work. So here's my answer. I know these things for a long time. So you define the category of non-commutative compact spaces. Category. It's by definition the category of system algebras, which is well defined. With the arrows reverse, you reverse all the arrows. That's the category of non-commutative compact spaces. So it makes sense as a category, absolutely no problem. So I said here is well defined. Just my notation might seem a bit, I don't know, might offend some of you guys who are very picky, but a non-commutative space, so it's perfectly well defined category. And that's my notation. Okay, believe me, it's better to use this notation. It's just a notation. Okay. Now, what will be the idea? Well, of course, this doesn't change anything. I mean, just algebras will be things like this, right? What you see here on the screen. I mean, it's kind of computation, so it doesn't bring anything new. It's philosophical. So we'll still be doing operator algebras, but this time no longer thinking at them as matrices, the operators, but rather as algebras themselves as being functions somehow. So we'll do our regular work. I mean, operator algebra, operator theory. But for instance, whenever we have a morphism, we'll think of it as somehow coming from the morphism at the level of non-commutative spaces in the other sense, and so on. Okay, so we study non-commutative spaces. In practice, it's of course operator algebra work. All this now up to some subtleties, because one basic thing that you'd like to do, for instance, you have a product of spaces. This should correspond to a product, tensor product of sister algebras, and there it's of course well defined, but then you have to complete it. The tensor product might be several norms there, and actually several tensor products. Okay, so you have to be careful when doing such things. But it works. So again, it's perfectly well defined. It's non-commutative spaces. They don't have points, but they have functions of them. These are the sister algebras. And on the story. Now, of course, all this is extremely abstract. So let's see some examples. Yes. So as the main example of a space, it's your soccer ball, right? So now, if you want to play some non-commutative soccer, you need these free spheres, okay? Real and complex. So we'll be doing things in real and complex because they're both important. So just take algebra generated by some x1, xn coordinates, self-adjoint, all of them. Sum of squares is 1 in the real case. In the complex case, the same thing, but we use this formula instead of xi. The square is 1. So these are just algebras. They're well defined because well, you have to check that the norm is bounded, okay, on such beasts, and then that's your inequality uses positivity here somehow. So the norm is bounded on the star algebra, if you want, constructed with these generators and relations. So that star algebra with that bounded maximal C star norm completely together C star algebra. So, and you can call these functions on the free real sphere, free complex sphere. Now, as the first results, you have this diagram. So you see what we have here in the four spheres, the classical ones on the left, free ones on the right. And the theorem is that the free ones appear as liberations of the classical ones, meaning that their classical version is just the classical ones. So what does this mean? It's something classical. You need to prove that these classical spheres appear somehow from these algebras by imposing commutativity, okay? That's what I'm saying. So just put a com here, meaning that the coordinate commutes. These are algebras, and we must prove that these are the algebras. Oops, there is a mistake, but typo here. There's no plus here, okay? No plus here, no plus here. So I want to prove this without pluses, and that's by Gelfand. I mean, all these are commutative algebras by Gelfand. Must be functions on some space. That space has coordinates, so it lives here in Rn and in Cn, respectively. Coordinates sum up to 1, their squares, we get the spheres. Okay, for some Gelfand. Very good. Now that we have spheres, let's look into the tori now. That's the next thing. So what's your torus? It's your donut. Okay. So after a soccer ball donut. So for if you're hungry for non-commutative donuts, that's what you have to do. So you take one of these four spheres or other things. There are some more complicated spheres. You model by relations, basically stating that the coordinates are unitary, but up to a factor, right? These guys sum up to n, sum up to 1, and there are n of them. So it's not unitary, but well, you have to put your n over n there. And you call this associated torus. So does it work? Yeah, of course, from the complex sphere you get the torus. If you do this, right, so in a complex sphere, the coordinates are unitary, so you get your donuts. And for the real sphere now, what does this mean? The coordinates must have absolute value 1 over square root of n. So in real, In complex, you have a circle, right? That's the solution. In real, you only have 2 points. So finally, you get a cube. This torus is actually a cube. So there's a bit of a terminology problem here. So I'll call this torus, but always in mind that when you apply this construction to real things, we'll get a kind of cube, okay? But let's call it torus. We'll see later why. That's the best terminology. Now, if you look at this, let's try to compute this tori for these spheres. And if you look at this, finally, up to a factor, of course, it's algebras generated by unitaries. So these are the group algebras, actually. So let's get now into group algebras. This will solve our problem. So take a discrete group, have the group algebra, just the span of all elements, put on in the involution, making all the group element unitaries. Then if you take the maximal norm, it's a C star norm, you can close the group algebra inside it and you get an algebra called C star of gamma. That's the result. So in order to prove this, the point is that C star of gamma embeds somehow C star of gamma. That's what you want to prove, that you have at least one norm which is faithful. So for that, use the left regular representation. Okay, of the group by left multiplication. That's well defined, well known, and this gives you the result. I mean, you have at least one norm which is faithful. So now you can take on the group algebra, algebraic group algebra, I mean, not yet closed. So you have that norm. Maybe you have some other ones. In any case, you can consider the maximal C star norm, which is bounded because the generator's group elements are unitaries, right? So it's bounded and completed with respect to that biggest norm called something called C star of gamma, group C star algebra. Now let's see some examples of all these. So my claim is that these are the tori somehow, the algebra functions on the free tori are of this form. But before that, let's get to some examples of group algebras. So when gamma is abelian, this is C star of gamma, of course, is commutative because group elements commute, right? So let's see what we get. We apply Gelfand, so must compute the characters of C star gamma, but you can delinearize, right? So these are the same as the characters of gamma itself. So finally, get the functions on the group of characters, the so-called Pontryagin dual, denoted with a hat. It's a compact group, okay? So this is a theorem when gamma is abelian, discrete. C star of gamma is the same thing as C of G, G being the compact group of characters, the Pontryagin dual. Which is very, very nice because now when you see this, you say, well, when gamma is no longer abelian, that's something that you might know. Maybe if you did some algebra, there are some groups which don't have enough characters. And this group of characters, the Pontryagin duality cannot work in an abelian case. But with our non-commutative spaces here, we can solve this problem. So we just say C star gamma, gamma non-abelian, fine. Because this is a C star algebra, I can always denote it C of G and say that G is gamma hat by definition. Okay, so the Pontryagin dual of a non-abelian discrete group is perfectly well defined as a non-commutative space, and that's its definition. So it solved a big problem, okay, that was non-trivial. Before, people didn't know how to do this. So that's a point, a very nice application of this Gelfand philosophy. Substance of all spheres and which are, we'll get later to the spheres, might seem important, they are important, but this really solves a problem in group theory, okay? We know how to talk about duals of arbitrary discrete groups, very nice. So let's back to tori now. So my claim is that the tori, yeah, that was the definition. So basically up to a rescaling, the generators must be unitaries. So in order to compute the tori, it's going to be group algebras, clearly. So just take what are the relations here. So you have the big sphere, the free complex one. And then you can have commutation relations or real relations, meaning coordinates are self-adjoint. So if you do this at the group level, well, here you get the biggest group, right, for the biggest sphere. So the dual of the free group of n generators. And now here you must assume that the coordinates are real. I mean, the unitaries are self-adjoint. You get Z2, okay? And now if you assume that these things are commutative, you get the torus in the cube. That's So on the left, these are things that we already had. These are the new results here. Proof, just trivial, you know, the theory. So very good. So that's what we have. Spheres, non-commutative tori. In general, gamma hat here is called a non-commutative torus. And that's why we call it torus, not cube. So non-commutative torus, by definition, is a group dual in this sense. And in particular, the tori associated to the spheres are of this form, okay? So very good. We have some beginning here of non-commutative geometry, and we'll do that later. We'll come back later in the next lecture doing some quantum groups, okay? So actually, these guys are quantum groups already. Talk more about this later. So summary so far, yeah, we have a definition for system algebras. That was the main result, Gelfand. We can do some non-commutative geometry with examples, spheres and tori. I'll be back later to this. Now, let's go back to what we wanted to do in the beginning. So I told you there are three theorems for system algebras: Gelfand, GNS, meaning that any system algebra is an algebra of operators, and finally, finite dimensions. So let's get now to this GNS thing, have it proved, okay, before doing this stuff, quantum groups. So we want to prove that any system algebra embeds into B of H. So how do we do it? In a classical case, H can only be L2 of X, right? So in the measure on X, and then of course you have an embedding by left multiplication. These operators are bounded because that's your inequality, it's trivial. So we're done. Now in general, well, same idea, but let's assume that A is arbitrary. We can write that C of X because that's how we like to do. These are these non-commutative spaces. But no, what's a positive measure? So X has no points. We cannot talk about measures. So what's the solution to this? Well, we can talk about measure, but we can talk about integration. So the integration is a functional on C of X. So for an arbitrary system algebra, we just need to talk about functionals, right? Having, of course, suitable positivity properties in order for measures to be positive. So this is my definition. Take a linear map on my system algebra. It's called positive when maps positive to positives. So here I'm using the theory of positive elements, of course. Yeah, that's a positive element. This is a number which must be positive. And also have a notion of faithfulness. So in the commutative case, that's what I was saying. We put C of X here. That's Rees theorem, I guess. Yeah, Rees tells you that these guys, these phi's are exactly the integrations with respect to measures. In general, now the philosophy is similar. So we'll work with this form and always think of them as coming from measures. So first thing to be done, this theorem, let's extend it to same thing. I mean, left regular representation, L to space. So if we have a positive linear form, or have your scalar product here, complete, get a Hilbert space, that's your L to space. Left multiplication defines a representation. All this is trivial. And the point now is that we want this representation to be faithful, right, for proving the GNS theorem. And this happens, of course, the measure must be probability measure, so it must be phi must be faithful in this sense here, okay? So what's left now, in order to finish, to have a faithful representation, must construct a faithful positive linear form, okay? So that's the construction, it's a bit technical, so what's the idea with all this? You see the conclusion. Yeah, you have a faithful positive form. That's what we want. So idea is to do like in the classical case. So you see, if you want to construct a measure on a compact space X, it's not obvious. So X is a sphere, is of course uniform measure, same for tori, or like other homogeneous spaces, you have a uniform measure, but the space is arbitrary, you're in trouble there. You have to do some functional analysis, something like that. So what's the idea is to take a measure at any point of your space, which is like positive around it, and then to sum these guys, or maybe make a zero sum for things to converge. That's going to be a probability measure on X. So it's annoying mathematics somehow. So here is the same. We have to do this kind of annoying mathematics, but with operators. So there's some spectral theory for doing all this. But it's the same idea, you see. On Norman elements, you have a positive form which somehow takes the maximum there. and then you will make a sum into it. So yeah, well, there are some computations here for proving all this. That's what I told you. So finding a Han-Banach and a Cesaro limit. So once again, the idea is that you do it at any point and then you sum the Cesaro limits. And well, maybe we won't get into this. I mean, it's really a bit technical and no need to learn this. Okay, this is a part which is a bit technical of today's lecture. You can always come back to it later. Okay, once you know a bit algebras, what they're good for, you're convinced that this is really worth learning, you can learn it. Okay, download the slides. If the slides are not enough, you have the link to my webpage or book. I have books there, everything, and links to other websites. Everything is on the web, okay? Quantum groups. So no need to go outside. YouTube blogs, there are many channels and everything. You can learn everything. So for the moment, I think, yeah, no need to focus on these things. So there's a proof. It's like in a classical case, and this holds, and all, we're done. So remember, the GNS construction was this. Once we have a positive linear form which is faithful, we won. This left multiplication representation on L2 is faithful. And now we have the existence or none. So GNS A appears as operators. Of course, in the separable case, this is separable. In the finite dimensional case, H can be chosen to be finite dimensional. All this happens from what we have here, technical things. So it's done. Okay, so once again, all this follows from this construction here. Okay, the old one, which comes from here. So it's not that complicated. Again, A, you want to take a system algebra, you want to see it as abstract algebra of linear operators of Hilbert space. In the classical case, the space can only be L2 of X, representation by left multiplication. Now, in general, we do exactly the same thing. So we need a positive linear form that somehow the analog of the measure, the integration. We define L2 space, left regular representation, and quarks, provided that the initial data, this phi, is faithful. The existence, like in the classical case, is a bit annoying, but you have a proof it's true. And with this, we're over. So very good. We have Gelfand and now GNS. Very useful results both. Now the third one, good news, is very simple, just one page. So that's a kind of self-proving statement. So if you make the statement long enough, you can say simply that the proof is this. Okay, that's a bit of a joke here, but it's good to know all these things. Okay, that's why I put them the theorem, the final theorem is 5 or maybe 6, but it's good to know these things. We'll use them later for when working on quantum groups and stuff like that, Peter Weyl's theory. So let's read it in detail. So I take a system algebra of the matrices, okay? So what we do, we want to prove that this decomposes as a direct sum of matrix algebra. So if you have your matrices, we want to prove that it's this plus this plus this, maybe by spinning by unitary. That's why I don't put equal here, it's isomorphic, okay? So how to do it? Well, these components, the blocks, I mean, you just take, write the units of A as a sum of minimal projections, right? These blocks will be these PAP guys. These are non-unit algebras. Okay, the unit is not the same. The unit here is P, these blocks, P1 up to PK. Now A, of course, will decompose as a sum of these blocks. Now each of these blocks, of course, because the projection is minimal, you have to work a bit. It's a matrix algebra. So finally, you have your sum of matrix algebras. Very good. So this was for a algebra of the matrices. It's just extremely elementary. It doesn't use anything. Okay. Now the same conclusion holds for any finite dimensional system algebra. It must be this. And here, best is to use the GNS theorem. Okay. So remember, if you have a finite dimensional system algebra, well, it's a subalgebra of matrix algebra, and that's what we say here with the 3. So you can apply 5 and get the results. So okay, we prove this too, that the finite dimensional system algebras are exactly direct sums of matrix algebras. So as a conclusion now, what we did today It's a lot of good work. Okay, so you need all these things, no matter what you do as mathematics or physics. These are extremely basic things. So sister algebras, norm evolution, this condition. Learn three things: Gelfand, commutative case means C of X compact space. GNS, which are Gelfand, Neyman, and Segal. These are algebras of operators. And infinite dimensions, these are direct sum of matrix algebras. Of course, as a remark, there are some connections here. I mean, this is related somehow to the spectral theorem. You see, if you want to, well, if you want to view C of X inside B of H, that's something we know. Maybe conversely, conversely, if you take a commutative subalgebra of B of H, say generated by a normal operator, by Gelfand should be C of X, so X is the spectrum, so of the operator. That's a spectral theorem, so you see we proved the spectral theorem too. Finally, it's quite powerful, these things, okay? In finite dimensions, well, those doing algebras kind of know this algebra, know these things, better upon theorem. So it's valid in more general situations, but yeah, these are the three things, extremely useful, all three. For more basic theories, so as I told you, it's a bit hard to get to the next level with these three results. And to get more complicated things, it's going to be hard. So instead of getting into a technical sister algebra book, I'd rather recommend, if you really love the subject, and I hope so, to get rather to a von Neumann algebra book. So these are algebras which are a bit different from sister algebras. They're close to the weak topology. Very related to physics and very beautiful stuff. But John von Neumann was a very big mathematician and very good. So yeah, that's my advice. If you really like these things, yeah, rather learn some von Neumann algebras. Okay, it's a very nice theory there, especially the original papers. John von Neumann, Alan Kohn. Okay, that's my advice. And then in what regards us here, so that's what we will need as technical ingredients. We'll use these three theorems all the time. So what we have this Gelfand theorem, AC of X. So we can write this in general with X being a non-commutative compact space. We already have spheres. Now we can play our non-commutative soccer with, no matter what that means. And we'll have some tori, which tori are group duals, and that's quite interesting. Group duals solves a problem. Group theory was the dual of an arbitrary group. We know what it is a non-commutative space. And these are related to the spheres up here inside. So I have a beginning of non-commutative geometry there. So the problem is now, as we have here, tori, what about groups in general? So what should be a non-commutative group somehow? Well, these are not non-commutative, are called quantum groups. So the idea will be that we'll do this quantum groups starting from the next presentation. Okay, guys, hope that you like it, and yeah, this is really very interesting things. Don't forget to go to some papers for Neumann, John von Neumann, Alan Kohn afterwards. It's worth learning all these things. For the quantum group things, just trust us. You'll learn it from us. Thank you very much, and see you soon.